Okay, I think we are ready to go. It's welcome to this EC Distinguished Colloquium, and I'm very pleased to be able to introduce our distinguished speaker, Professor Vince Poor, who is coming from Princeton, but he's very well known here on this campus because he was a faculty member here. After receiving his PhD from Princeton, he joined the faculty in late 1970s, and he was here until 1990 when he moved back to Princeton and also became dean between 2006 and 2016. And he's a named university professor at Princeton. He's very well known in the general systems area with fundamental contributions to information theory, communications, signal processing, and even though not on his bio, I would say also to control. And he has, in fact, we have collaborated quite a bit when he was here as a faculty member, as well as after he went to Princeton. And he has also worked on game theory, on different aspects of game theory, both cooperative games as well as non-cooperative games, with applications to a very broad set of areas, and more recently to the smart grid. And he's going to, I believe, talk about some of those applications here during the talk. He is very well recognized in the international community, scientific community. He's a member of the National Academy of Engineering, National Academy of Sciences, is a foreign member of the Royal Society of Britain, as well as a foreign member of the Chinese Academy of Sciences. He has several other academy memberships, as well as honorary doctorates and professorships from different institutions. So I don't want to take all the time. I could spend the full hour actually introducing Vince, but I want you to have the opportunity to hear him, and it's a great pleasure again to have Vince here.
Thank you, Samir. Good afternoon, everyone. Can you hear me in the back? Oh, I got to turn it on. I'm an electrical engineer. I should know that. Okay, now, good. Okay, well, good afternoon, everyone, and thank you, Tamir, for that kind introduction. Some of it was even true, I think. So. It's really a pleasure to be back in Urbana. I always enjoy coming here. I spent 13 years here. My children were born here. I would be more of a pleasure on a nicer day, but it's always still a pleasure, and to see my old friends here and so forth. So I'm really delighted to have this opportunity to speak here today. You know, what I'm going to talk about today is some fairly basic ideas relating to the Internet of Things. So, you know, every 10 years for the last, I guess we're talking about 30 or 40 years now, there's been the development of a new generation of mobile communications, okay? The first generation was in the 1980s, and a lot of the work was done here. Colleagues here worked on a lot of the early ideas for that, and over the years they have continued to. The first generation was analog voice system. Wasn't very good. Many of you weren't born then, but if you had a cell phone back in those days, you'd be very frustrated with it. Second generation was digital voice and texting. Third generation was digital data. Fourth generation was really, I guess I would say, the smartphone and streaming data and that sort of thing. And now we're working on the fifth generation, and it's going to come out soon. You may already see hype in the media about the fifth generation, but it's going to be a while. All these generations roll out typically around the time of the Olympics, And then what rolls out then is not exactly what's going to happen, but it's an early phase. And then over the decade, things come out. And by the end of the decade, when you're getting ready to launch the next generation, usually a generation is fully formed. So one of the things about the 5th generation, though, different from all the previous generations, is that in all the generations 1 through 4, the end users of the network were human beings. Okay, so this was the main end device of the network, a cell phone, and now it's a smartphone. But in the 5th generation, there's another type of network, which is the so-called Internet of Things, which I'm sure many of you know about. I know you have a course in that here, in which the end users are actually machines, not or other objects, not people. Okay, so in itself, that doesn't seem like a big change, but it does. It actually creates a new regime of performance, and I'll talk a bit about that in a minute, in which the sort of prior fundamentals don't apply anymore. So except for the 1st generation, generations 2 through 4, a lot of what happened there were guided by the principles of information theory, developed by Shannon in the 1940s, and of course improved and enlarged and expanded over the years by many researchers. But it told us what were the fundamentals we could be, what were the limits we could be looking for in those generations of mobile communications. But in the 5th generation, there are some limitations that preclude the use of sort of classical ideas of information theory. So the question I'm going to talk about today, or the issue I'm going to talk about today, is if we have IoT networks where we have new paradigms in performance requirements, what kind of fundamentals can we develop for that? Okay, so I'm not going to talk about IoT, the practical side of IoT today. What I'm really going to talk about is fundamentals. What can we say about the problems that arise in IoT at a very fundamental level? So, of course, this is only part of the story. There's a lot of very practical things to worry about, more practical things to worry about than they are what I'm going to talk about today. But somehow we need to think about these fundamentals, and that's what I'm going to talk about. Okay, so first of all, what is the Internet of Things? Well, there we go. Well, it's the internet where the end users are things rather than people. So there are many applications, and some of the applications include agriculture. So we're in the middle of the Corn Belt here, so that's a big important thing here. But things like robotic surgery, automated driving, automation in factories, telemedicine, you name it, basically any kind of technological aspect of society can be instrumented with sensors and actuators and be put on the network so that it can be improved. Okay? So one thing about this is that there's only 7 billion people or so on the earth. So the number of these that can be active is kind of upper bounded by that. Okay? But the number of things is, another couple orders of magnitude, right? So when you think about the Internet of Things, you're thinking about maybe hundreds of billions of devices, okay? So very large number of devices, massive connectivity. Also, it's mostly going to be wireless, not all wireless, but I'm thinking of it being wireless because most of these devices are going to be out there by themselves, communicating back from taking some measurements or what have you, and they're going to be doing that wirelessly. So the Internet of Things, very important to society, okay? But it's going to present some challenges, and here's some characteristics that dictate those challenges, okay, or inform those challenges. So one is massive connectivity, as I already said. The idea is that there are going to be many, many devices. In this room, there are a lot of human beings. You could all be on your cell phones at once. Maybe you are. But there's still a limit. Whereas in a factory, there could be so many things that it would be another order of magnitude of end devices. Also, there they're going to be connecting randomly. Okay, it's not like a connection like you have in your phone where you connect and you're on the phone or what have you. High energy efficiency. So a lot of these devices are going to be placed remotely. They're going to be simple devices that need to have really long battery lives because you don't want to change the batteries on 100 billion devices all the time. And low complexity because they don't have to do as much as this is. This is really a computer, but the devices we're talking about here may be $10 devices that are just out there collecting data. Okay. The infrastructure would typically be very light because of so many devices. You can't have a base station handling necessarily all of these devices in massive connectivity. And two important things for what I'm going to talk about today is that most of the communication of these devices are going to be in short packets. That is, the messages are going to be short. It's going to be things like the temperature is 22 degrees, or turn right or turn left if it's a vehicle, or you've got a vehicle coming up behind you from a radar, say. And low latency is very important. So I don't know if I have a slide on this, but I'll just say that on this device, where a human being is on the other end, humans can tolerate latencies, meaning delays, of 100 milliseconds or even up to 200 milliseconds without even perceiving it. So psychologically, if you're talking on the phone and there's a delay between you and the person you're talking with of 100 milliseconds or 150 milliseconds or so, you won't even notice that. And the network is designed around that tolerance. So, but for machines can tell within a millisecond latencies. And if you're thinking about something like an automated driving, say self-driving car, or any kind of automation in a car, in 100 milliseconds, a car going down the freeway can go a long way. So you really need to have very, very short latencies when you're talking about communicating between things in many applications. Robotic surgery is another example where you need really low latencies. Okay, so this part of it, in fact, all of these things really drive the fundamentals. They're not really fundamentals for all of these things, and we'll talk about some of them today. Okay, so the theme then today is what is the role of information theory in this area? Okay, and you'll see why traditional information theory may not be as applicable in this regime as it is in sort of more classical fields. And I'm going to talk about two topics in that general area. One is security, and I'm going to talk about physical layer, so-called physical layer security, which many of you may be aware of. And this is a way of getting around the fact that the infrastructure is light, okay, and also that the complexity is low. And I'll talk a bit more about that in a minute. And then the other question I'm going to address is latency. And that's going to be in the form of what's called finite-blocklength information theory. So information theory, for those of you who know it, know that it's an asymptotic theory as the number of times you use the channel goes to infinity. Okay? Now that makes a beautiful theory which works a lot for when you have long latencies and so forth you can tolerate. But when you have very short latencies, that theory no longer is applicable. So the question arises, what can we do? Can we derive fundamentals for finite block length when we're not in the asymptotic regime? So that's the other thing I'm going to talk about, and I'll motivate it a little bit more when I get to it. So let me start by then with this idea of physical layer security. So first of all, traditionally in networks, security is handled at the higher layers. So networks are organized in layers. The top layer is the application layer where we as humans interact with the network, so web browsing and talking on the phone and texting, those are all applications, and of course apps on your phone. And that's really typically where encryption is handled, security is handled, and typically in terms of data confidentiality, the way of providing security is encryption, okay? Now, when you have a massive number of devices and the infrastructure is light and the devices are low cost, meaning low complexity, and they have low latency, all those things work against encryption. Okay? First of all, for the massive number, you have to do key distribution of some sort. And if there's not much infrastructure, it's hard to handle things like that. If you want to use public key, you need computational power and you need computational time, and those work against low cost and low latency. So physical layer security is a way of trying to provide some level of data confidentiality and other aspects of security by exploiting imperfections in the physical channel rather than computational difficulty, which is what most encryption is based on. Okay. So the idea behind physical layer security is that you already have to do channel coding no matter what to provide reliability. So the same kind of coding can be used to also provide some level of security. Okay, so that's the idea of physical layer security. You don't increase complexity. You may not get the bulletproof security of encryption, but you can get some security just from the physics of the radio channel. So physical layer security is based on so-called information theoretic security, which goes back to Claude Shannon, like most things in information theory. And Shannon was the first one to introduce the information theoretic ideas into the study of security. Okay? And he looked at this problem where you have a transmitter, Alice, who wants to send a message reliably to a receiver, Bob, and at the same time keep the message secret from an eavesdropper, Eve. Okay? And in this model, there's no noise. Everybody sees what's transmitted perfectly. Okay? Now, Alice and Bob share a secret key. So they share a secret that Eve can't see. So this is an encipherment system, so a cipher system. And Shannon asked the question, if I want the so-called mutual information, that is the information leakage about the message M to Eve to be 0, what properties does the secret key have to have? Okay? And he showed that, in fact, you can get perfect secrecy in such a system, but it requires a one-time pad, meaning that the key has to have the same entropy, that is randomness, as the message itself. Okay? Now, Shannon was interested in a system which was a radio telephone system where the key, this was between Washington and London, where the key was transmitted on a record by a beefy guy with a briefcase strapped to his wrist on an airplane. Okay? But if this is a wireless channel, you have to use the same resources to distribute the key that you do to distribute the message. So if you can distribute the key with as much entropy as the message in secrecy, you could just transmit the message in secrecy. So this is not a very useful model or a very useful result for a wireless network. So another information theoretic approach to security is by this guy, Aaron Weiner. Both of these people working at Bell Labs. This is like 25 years later, though. And Weiner had the idea that, well, in reality, communication channels have noise. And so Bob and Eve will typically be at different places. And so the channel, the noisy channel between Alice and Bob, and the channel between Alice and Eve will be different. And so can that difference be exploited to provide reliable communication to Bob while keeping a message secret to Eve? So he looked at this idea of looking at the reliable rate to Bob and trading it off with the so-called equivocation at Eve. So equivocation is just a measure of information leakage. So this is actually the conditional entropy of the message. Again, entropy is just a measure of randomness given the measurements that Eve sees at the output of her channel. Okay? And he defined something called the secrecy capacity, which is the maximum reliable rate for which the equivocation at Eve equals that rate. Okay? So this means that at that rate, you're transmitting in perfect secrecy. And look at the maximum of all such rates, you get the secrecy capacity. And Weiner, like Shannon, so Shannon had good news and bad news, right? Shannon's good news was that you can transmit in perfect secrecy in an encipherment system. The bad news is you've got to have a key that's as rich in information as the message itself. Weiner had good news and bad news too. His good news was that A system like this, even without a secret key, can transmit in perfect secrecy and reliably, so the secrecy capacity can be positive, but if and only if the channel to Eve is degraded in a certain way relative to Y, to the channel to Bob. So the idea, you might think about this as say, well, the signal-to-noise ratio at Eve is lower than the signal-to-noise ratio at Bob. Okay, so that's good news, bad news. Good news, positive secrecy capacity. Bad news, you can only get it when Eve is degraded relative to Bob. Okay, so this is a long time ago, 1975. Again, this was before widespread mobile communication. So Weiner was thinking about telephones. He wasn't thinking about mobile communications. But this turns out that this is a very useful theory for what I'm going to talk about today. So now, in the last, I would say, decade, there's been a resurgence of interest in these ideas. Okay, and why is that? Well, that's because of the wireless channel, right? And now, particularly with the Internet of Things, we're in a situation where we can no longer rely on encryption to provide data confidentiality, so we need to look for some other resource, okay? Now, in general, the lessons were taught by Shannon and Weiner, both of them have the situation, give the situation where somehow the legitimate receiver has to have an advantage over the eavesdropper in order to get secrecy. So in the case of Shannon's model, you need a shared secret, the key. And in the case of Weiner's model, you need a better channel. Okay, so one way or the other, you've got to have something that the eavesdropper doesn't have. Okay. Well, it turns out that the physical properties of radio propagation provide opportunities for this. So what are the physical properties of radio propagation? Well, diffusion, you transmit a signal and it goes out everywhere. And superposition, which is just a linearity property that if two radio waves arrive at your receiver, they add together, okay? So those two properties cause fading, okay? That is, signals, because of reflections of objects, fade when they come to a receiver. And if you have two receivers in two different places, the fading is different, okay? And it changes over time. So the fading provides natural degradedness over time of an eavesdropper, okay? So that's one way you can use a radio resource. Just use fading. And we know from other things that fading is very advantageous for radio transmission. In the 90s, so-called MIMO systems were discovered, and we found that fading can give us a lot of capacity and reliability. Well, it can also give us security. Interference. So we can use interference to provide active countermeasures to eavesdropping. This is the superposition principle. So we can jam an eavesdropper, and that degrades the eavesdropper. So there's another way to do it. We can use spatial diversity, so we can use multiple antenna systems or systems with relays to create so-called secrecy degrees of freedom, okay? So those are all ways that we can use radio properties to degrade an eavesdropper. We can also note that the channels between the transmitter and receiver, the legitimate transmitter, the transmitter and the legitimate receiver, is a random channel because of fading. And so but it's reciprocal. That's another property of radio channels. That is, this channel from Alice to Bob is the same as the channel from Bob to Alice. It's a linear channel. So they can both see that randomness, and so it's a degree of common randomness, so they can use that to generate a secret key. So common randomness can be used to generate a secret key, and that comes from the physical properties of the radio channel. Okay, so this allows us to get, these resources can be used to create opportunities to get, to transmit messages with confidentiality, okay, just using the properties of the radio channel, okay? So the first of them are ways of degrading the eavesdropper. The third one is really, the fourth one is really a way of getting a secret key that can be used as a one-time pad, okay? So we can use, the first three give us Weiner-type capacity. The fourth one gives us Shannon-type capacity, okay? So I'm not going to go into a lot of detail here. The idea is that when you have a channel, then what you'd like to do is, just like in the case of regular channel capacity, you want to find the possible region of all possible rates at which you can transmit in perfect secrecy, so-called secrecy capacity regions. And wireless networks are like organic molecules, okay? To study organic molecules, you study all these little bonds, and that helps you understand the whole molecule, bigger molecules. Well, to study wireless networks, we study these small networks and try to use them to understand the properties of larger networks. So the elemental networks of wireless are the broadcast channel, where you have one transmitter and multiple receivers, the multiple access channel, where you have multiple transmitters and one receiver, interference channels, where you have multiple transmitters and multiple receivers, plus other channels, relay channels, where you have relays, multiple antenna channels, so-called MIMO channels, where you have multiple antennas on each transmitter and receiver, and so forth. And over the past decade, there's been a systematic study of the secrecy capacity regions of all of these elemental channels and implications for larger networks. And I'm not going to go into detail. I'll just point out that there's a survey. It's now 2 years old in the Proceedings of the National Academy of Sciences that sort of covers what happened up until that point. Of course, there's been a lot happening since then, but if you're interested, you can take a look at this survey. There's also the idea, as I said, of generating key from common randomness. And there's a lot of ways of doing this. This actually goes back to, some of them go back to the 1990s, so it's an older area really. But basically you can generate a key by discussing in public some things between the transmitter and receiver. Even if the eavesdropper can see the public discussion, because the eavesdropper can't see the randomness of the channel between Alice and Bob, she still can't distill the same key. So there are a lot of ways of doing that. I mentioned channel reciprocity, where the two legitimate parties distill key just from the random behavior of the channel. You can also use relays to assist in key distillation, and they can either be trusted relays where they know what they're doing and they know they're on your side, or they can be oblivious relays where they're just relaying things in a certain way, but that creates another source of randomness. If you have active eavesdroppers, you can only really use channel reciprocity. Some of these other things can be defeated. And again, I'll just point to a survey. This is in a book on physical layer security about key generation from random channels. Again, this is a little bit older. There's been work since then, but this is a place where you could start if you're interested in this. Well, this is a very rich area. Physical layer security ties into a lot of different areas of communications and other fields. First of all, physical layer security is about creating capacity regions. So once you have a capacity region, you need to find codes that hit that can hit points in that region. So code design is a big part. This is actually very active now, designing codes for physical layer security. Cryptography, of course, because key generation and management. Well, key generation can come from a physical layer core. Also networking, because when you have a capacity region, then you need to have a scheduler that schedules messages in and out of that region. Okay, if you have multiple users, somehow you have to decide how you're going to use that capacity. So there's a sort of cross-layer issue of networking. And then game theory. There's Professor Bashar mentioned game theory. Well, this is an adversarial problem. You've got Eve and Bob are adversaries, and there are some game theoretic aspects of that as well. So it plays into a lot of other areas. So it's just kind of a rich area of study. I'm going to mention some other IoT security issues. I was talking about data confidentiality. There's a lot of, security is a big area. There's a lot of things in security that are important. One is authentication. That is, how do you know that who you're talking to is who you think you're talking to? And there's been work in that area. I'm going to say a little bit more about each of these. Another is when you have a mobile ad hoc network, which you might have in the Internet of Things, there might be some malicious nodes in there. And you might ask the question, how many malicious nodes can we tolerate and still be able to communicate confidentially? Okay. Another problem is smart grid. Professor Bashar mentioned that I had done some work in this area. And there's a lot of information theoretic thinking about how to protect smart grid against stealth attacks. So these are usually attacks on the sensing systems of smart grid to make it to confuse the operators of the grid into doing unfavorable things to the grid. And then also sensor networks, which are, this is not exactly information theoretic, but it's close. This is looking at the Cramer-Rao lower bound, which is a type of statistical information. We can also look at attacks on sensor nets, spoofing attacks and man-in-the-middle attacks. So these are not, none of these are really about data confidentiality. They're really about other kinds of bad things that can happen to networks. And information theory can guide all of these, and I'll just very briefly mention these. This is a relatively old piece of work, 10 years old, looking at authentication, okay? And there are two kinds of authentication attacks. One is impersonation, where a bad guy, an opponent, tries to impersonate a legitimate terminal and transmit faulty data to a receiver. And the other is a substitution attack, where the opponent actually replaces a legitimate message with its own message, okay? And it turns out we can look at this type of situation in the same way we look at Weiner's model. If the channel from S to O is not less noisy than the channel to S to R, then we can upper bound the probability of success of impersonation and substitution attacks. Actually, we don't upper bound them. We can say exactly what they are. They're 2 to the minus L, where L is the length of the transmitted messages, times the mutual information between the source and the receiver. Okay, so we get a very clean result here about the possible success of impersonation and substitution attacks in authentication in wireless channel. Mobile ad hoc networks are networks where the communication, first of all, ad hoc networks are networks where the communication is peer-to-peer rather than being up to an access point. And a question of interest is when you have a mobile ad hoc network, again, you may have some malicious actors in that network. And the question might be, how many malicious nodes can you tolerate and still have positive secrecy rate in such a network, okay? And there has been some work in this area. This is actually Yingbin Liang, who's a former graduate student here at Princeton, at Illinois, and she was a postdoc at Princeton, one of Professor Viravalli's former students. And she looked at this problem and showed the following things. There's sort of two regimes. If the number of malicious nodes grows at the square, little o, so little o at the square root of the number of total nodes, d is just the communication diameter, that is the number of malicious nodes is small, then type 2 packets dominate the errors or the eavesdropping, and two-hop schemes, meaning schemes that have to go through at least 2 terminals to get to their destination. And the secrecy capacity is basically the same as if there were no malicious nodes there. So if you don't have enough, if you have a small number of malicious nodes, basically it doesn't affect the secrecy capacity at all of a mobile ad hoc network. On the other hand, if you have a lot of malicious nodes, so here where they're root in, same here, but also times a polynomial in n, so now the number of malicious nodes is large, then one-hop packets dominate the eavesdropping because you got a lot of nodes in there. And the secrecy capacity depends really only on the number of, it's on the order only of the number of malicious nodes, 1 over m. So if you've got a lot of them, you're not going to have much capacity, okay? So there are two regimes here that inform how secure this network can be based on how dense you think the eavesdroppers are. In the smart grid, the stealth attack, one way to think about it is it's trying to trade off the mutual information between the grid state and the operator's observation. So the grid state tells us something about Typically you look at the phase angles at the buses in the grid. That's the grid state typically. And the operator is trying to keep track of that to operate the grid. So an attacker would like to make that small, but at the same time, the attacker doesn't want to be detected, because if the attacker is detected, then some countermeasures can be taken. So the trade-off between the success of the attack, measured by the mutual information between the grid state and the operator's observations, and the probability of the attack being detected. The more successful the attack is, the more likely it is to be detected. Because the resources needed are greater. And this is some problem that can be studied information theoretically. I'm not going to talk about this curve, just to say that here's lambda is a trade-off parameter, and you can see that here we have the mutual information, which gets better as the trade-off parameter gets large, where the attack probability gets worse. So there's the trade-off. Again, just very briefly. And then finally, I'll just mention another problem, which is a sensor net, which most IoT networks involve sensor networks, at least a part of the network. And these can be attacked two ways: spoofing attacks, where physical data is altered, or man-in-the-middle attacks, where reporting is altered. Okay, if you look, and you can look again at this problem in terms of typically you're trying to estimate some parameter. Okay. And so you can look at, for example, the Cramer-Rao bound on the estimation of that parameter, and see how do these type of attacks affect that bound. So again, here's another way that we can use information theoretic ideas to try to understand the security of Internet of Things. Here, this is just showing, what this is showing is basically what happens if you have a man-in-the-middle attack. And if you use the fact that the attack is not always perfect, how much lower Cramer-Rao lower bound can be relative to a bound when you just ignore data that's been attacked. So it's just an example of what you can look at using information theoretic criteria. Okay, so I'm going to try to keep us ending on time, and so I want to shift gears now and talk about the other area that I mentioned, which is finite block length information theory. And again, we've got a picture of Claude Shannon. We always have to start with that. So traditional information theory, Shannon worked on the point-to-point problem, where you have one transmitter and one receiver, and then enlarged that to network information theory. He worked on two problems: data transmission and data compression. And then this was expanded into network information theory, where you look at broadcast, multiple access channels, relay channels. The wiretap channel is an example of a network. And compression, data compression, we also looked at secure compression, similar to secure transmission in the wiretap channel. But one of the things about Shannon's work is that it's asymptotic. That is, what Shannon tells us is what happens when delay is not important. If we can wait forever, we can have an infinitely long code. What is the best we can do in a channel? Okay, that's Shannon's capacity. Now, the benefit of that is it really characterizes real engineering problems in terms of very elegant mathematics. Okay, and as I said earlier, that's really driven thinking about generations 2, 3, and 4 of wireless systems, is what are the Shannon limits of these radio channels. But if you have IoT, you're worried about low latency. Okay, in fact, you're really worried about high reliability and low latency. So that's one of the sort of regimes that people look at. So you can't really you want to look at high reliability. That is, you'd like to know what are the fundamental limits. But you'd like to know that not in the asymptote, you'd like to know that for finite block length, because you're going to have short packets, low latency. So when latency creeps in, you can really no longer think about the asymptotics of Shannon. So what can we do here? Okay, well, I'll just remind you, for those of you who studied information theory, about sort of one of Shannon's basic results, which is the Shannon capacity. Here you have a really basic channel for data transmission. You've got a source which wants to transmit a source symbol W, which can take one of m possible values. And m, so 2 to the m, log 2 of m is the number of bits that are being transmitted here. There's an encoder that maps the source symbol into a vector of n channel symbols that are put into the channel. So we use the channel n times. And then out of the channel comes a vector of channel outputs, y. And that goes into the decoder, and the decoder tries to recreate the original source. And Shannon's capacity tells us the largest rate in the asymptotic regime, when the block length n, the number of channel uses, goes to infinity, and the error probability, that is the probability of symbol error, probability that the decoder output is not equal to the source, goes to 0. And that rate, so the largest rate would be log 2 of m. So the rate is log 2 of m divided by n. So you look at that as n goes to infinity. And he showed that the largest such rate is actually determined by the mutual information between x and y. So x is channel input, y is a channel output. Mutual information is a measure of similarity between the two. And you maximize that over the probability distribution of the input, and that gives you the channel capacity. So a really beautiful, simple result. Okay, driven a lot of thinking about data transmission. Okay, what about with finite block length? Well, with finite block length, we've got the same model, but now we've got to worry about the number of channel uses being finite. And by the way, we also have to worry about the fidelity not being perfect, because if you have finite block length, you're not likely to get perfect symbol error probability, okay? So here in the finite block length case, we're interested in so-called NM epsilon codes. So an NM epsilon code is a code that can transmit, that we can use to transmit a source with m values in n channel uses with fidelity, with error probability not more than epsilon, okay? So an NM epsilon code. And then a fundamental limit of a channel is the maximum m such that there's an NM epsilon code. For a given block length and error probability, we'd like to know the maximum number of bits we can send through this channel, okay? That's this fundamental limit. So log of that divided, log 2 of that number is that number of bits. And if we divide that by n and let n go to infinity, we get Shannon's capacity, right? But what if we can't let n go to infinity? What can we do? Well, it turns out, in this work of Yuri Polyansky, who was a graduate student at Princeton, now at MIT, in his thesis, he showed that this log of this value is n times the channel capacity, so this is Shannon's result, minus a correction term, which is the square root of n times v. V is a new parameter, times the inverse of the tail of the standard normal distribution evaluated at epsilon, plus higher order terms. And generically, these higher order terms are log n, but they can be higher order for different kinds of channels, but generically they're log n, okay? So C is Shannon's capacity. Shannon's capacity is actually the expected value of a random variable called the information density, evaluated at a random variable that input random variable that has the maximizing distribution in the capacity that I told you about before. So that's the mean of that random variable is the capacity, and the variance of that random variable is something we call the dispersion, which determines the next higher order term, okay? And it turns out that these first two terms give a pretty good approximation to the actual possible maximum capacity for finite block length. So just look at that. Here's an example. This is an additive white Gaussian noise channel, a channel where the impairment is additive white Gaussian noise. The work of Yuri's work shows upper and lower bounds on this m star. And if we look at log of m star and divide it by n, asymptotically it's going to be the capacity. So for these particular parameters of signal-to-noise ratio and symbol error probability, the capacity is 1/2. But what we're seeing here is an upper and lower bound, so a converse is an upper bound and achievability is a lower bound, on the actual channel capacity for finite block length. So this is versus block length. We know it's somewhere between those two. And this dotted line, or dashed line in here, is an approximation based on that formula I just gave you, okay? So you can see that for small block lengths, 100, 200, which is not unreasonable for Internet of Things, there's a big gap between the actual capacity you can achieve and what Shannon would tell us. And in fact, it's kind of interesting that even for block length 2000, there's a gap. But down here, where we're thinking about Internet of Things operating, the gap is pretty big. This is for the additive white Gaussian noise channel. We can also look at the so-called binary symmetric channel. And again, we choose probabilities and crossover probability and symbol error probability to give us the asymptote of 1/2, so Shannon capacity 1/2. And again, we get upper and lower bounds that tell us somewhere in here is the real capacity, and for small block lengths, it's a long way up to Shannon capacity, okay? So we can use this for certain things. So an important thing now in the Internet of Things is the trade-off between energy efficiency and spectral efficiency, okay? And if you use Shannon capacity, you get one trade-off, this little red line here. But if you start using the finite block length information theory, and I see here I didn't put the block length, but this is for, I think, block length 14, so it's a short block length. You get a quite different story depending on what kind of fidelity you want. If you want really good fidelity, you're going to lose a third of energy efficiency, at least at the very low end of spectral efficiency, which is the best place for energy efficiency, and you're going to lose a lot throughout this regime, okay? And in fact, in the 5G standards that are being developed, they actually come in at about 1/2 the energy efficiency of the asymptote in terms of what they're talking about in the standard. So this kind of thing actually mirrors very well what's been observed also in practical systems. Well, we can also look at physical layer security in the finite block length regime because Weiner's work is also asymptotic, okay? So what about physical layer security? Well, in the infinite regime, we have results for the wiretap channel. In the finite block length regime, we have to modify those results. So basically, if we have a wiretap channel, we have Alice, we have the channel, we have Bob and Eve as before. We want W hat should be as close as possible to W. So we have an average error probability we're worried about. We're going to use the channel n times. And we have to worry about leakage at Eve. So there's an upper bound on leakage. Now to get Weiner's capacity, we would let epsilon and delta go to 0 as n goes to infinity. But if we keep those finite, then we've got something analogous to what I showed you before from Yuri Polyansky's work, which is the rate, the maximum secrecy rate at a given block length. Okay, so we want to bound the error here, the leakage here for block length n and find the maximum rate for that. Okay, so it's analogous to what I showed you for the regular data transmission capacity. And again, now it depends on the type of wiretap channel. We don't have a universal solution, but this is a wiretap, semi-deterministic wiretap channel where the wiretapper has a binary symmetric channel and the direct channel is noise-free, okay? And delta epsilon are 10 to the minus third. So delta is the upper bound on leakage, epsilon is the upper bound on symbol error probability. And we can get a formula very similar to what we saw previously. Depends again on the second order term depends on V, the dispersion, and it depends now on delta and epsilon, okay? And now the higher order term is still log n over n. And here's an example for this channel. Here's the block length, the secrecy rate. These numbers are chosen so that Weiner's secrecy rate is 1/2, or secrecy capacity is 1/2. But here we see, again, converse and achievability and approximations, but it all tells us the same story, that for low block lengths, there's a lot of there's a gap between, pretty big gap between the secrecy capacity and the finite block length secrecy capacity, okay, somewhere in there, okay. Now, these ideas of finite block length capacity have carried over into these network models too. Here is what's known is a lot less complete than in the case of the infinite link secrecy capacity, for example, or in the case of point-to-point channels for finite block length capacity. But for the two main channels, the multiple access channel and the broadcast channel, there has been some good work in this area. For the multiple access channel, for the Gaussian multiple access channel, there's a very complete result. Complete result on achievability, which comes very close to an upper bound, so we pretty well know where we are, and there's a big gap again between the outer region of the capacity region of the multiple access channel and the actual finite block length regime channel. And for the broadcast channel, it's a bit, there's a bit less known, and just in fact for the broadcast channel is less known for even for the infinite block length case, so naturally there would be for this case, but there's still work there as well, okay. I'll just mention another, it's 5 o'clock, so I'll try to wrap up quickly. So I'll just mention another problem of interest here very briefly. Another aspect of the Internet of Things is the massive connectivity. So in a classical multiple access channel, where you've got a fixed number of transmitters and a receiver, usually we analyze that by letting the number of users k be fixed and the block length n go to infinity, okay? And the so-called mini-access channel, also called the massive multiple access channel, the number of users grows with the block length n. So k, the number of users is no longer fixed, okay? And this is like the, this sort of models the massive connectivity of the Internet of Things. And there's been work on looking at the latency that occurs in such networks measured by the latency per user, which is like the number of, the block length divided by the number of users, okay? And of course, if k is fixed, then positive rate is possible, that is some rate. But it turns out that for different types of growth of the number of users in the block length, we get different stories in terms of whether this channel can support reliable communication. So if the number of users grows linearly with the block length, it turns out that the system rate, that is the sum rate of these channels, is the same as if the if the number of users was fixed and finite. If the number of users grows polynomially in the block length, the system rate decreases, but it's still positive, so it doesn't kill the throughput. On the other hand, if you have supermassive connectivity where the number of users grows exponentially with the block length, the system rate is 0. So there's a limit on how massive it can be, system can be, and still get positive transmission, as you would expect. Okay, this just quantifies that. Just mention very briefly another approach to latency, which is age of information. Okay, so age of information thinks about latency from the point of view of the receiver. And basically, the age of information is defined typically if you have, say, a sensor system, taking measurements, sending them through a channel to a monitoring device. Age of information is the time since the latest measurement has reached its destination, okay? So this measures latency, again, from the destination's perspective. And in the case of a sensing network, it really is assessing the freshness of data. So it's an important criterion in addition to distortion, right? So in addition to symbol error rate, you might want to also think about how fresh is the data. So if it's a, say, monitoring the climate or monitoring weather, you don't really care today to know what the weather was yesterday, right? You want to know what the weather is today. So freshness of data is another measure of the quality of data, and age of information quantifies that, okay? So this is a a good metric for real-time sensing applications, okay? And why would you care? Why wouldn't you just send the data as soon as you get it? Well, it's because of this issue of energy efficiency. So you might have, your sensors might be using energy harvesting. It might be harvesting energy from the environment. So it may not always have enough energy to transmit the data when it receives it. So there's a trade-off between energy use and age of information, energy use at the transmitter and age of information at the receiver. And these kind of trade-offs can be looked at using not only information theoretic issues, but also queuing theoretic issues as well. So I won't get into that because I'm out of time. So let me just wrap up then. So the basic idea of today's talk is that information theory, maybe rethought, can help us understand some of the fundamental limits on security and latency in IoT type settings. For security, the issue is complexity and lack of infrastructure, right? And maybe also lack of energy. And that challenges traditional methods of providing security. But we saw that the wireless physical layer, the radio channel, can offer ways of providing some degree of data confidentiality. And this is a very well-developed theory for basic prototype network models, although there's a lot of work needed to make this practical. There are prototypes, there are companies working on this, but it's not really embedded in practice yet. For latency, you know, we looked at this idea that latency is much more important in machine-to-machine type applications than it is in more human-to-human applications because of lower tolerances for latency in machines. And so now we have to worry about the fact that the fundamentals that we know from Shannon don't really hold anymore. So it gives us the idea that we need to look at a new kind of information theory for finite block lengths. Okay. And then I also mentioned briefly age of information. Okay. So I'll just, you know, as a caveat, everything I've talked about today is really just a theoretical construct, right? There's a lot of other things to think about in latency. First of all, there's a lot of latency in other layers of the network. It's not all just in the physical layer that I've talked about today. So interactions with higher layers is important. Also, scaling laws for large networks. We saw that for MANETs, right? Or MANETs, the scaling law for physical layer security. But, you know, really these are problems that need to be looked at for all large networks because of the massive connectivity. Also, I mentioned this earlier, but what I'm talking about today are fundamental limits. And just like in the case of classical Shannon theory, once you have the fundamental limits, you've got to start finding practical coding schemes. And in the case of large block lengths, we've gotten almost all the way to Shannon capacity with LDPC codes and so forth, polar codes, more recent development. But in these other areas, we still need to look at these fundamental limits, particularly for finite block length and for secrecy capacity. And also, there are a lot of other aspects to security, just like there are a lot of other aspects to latency. We have to worry about signatures, certificates, all kinds of other security primitives that need to be examined in these contexts. So the basic bottom line here is there's really a rich area here with a lot of work left to be done. And I think important work in terms of trying to understand the Internet of Things and what its limitations are. Okay, with that I'll stop, and I don't know if we have time for questions, but thank you.
Yes, we can take some questions.
Yeah. Oh.
Yes.
One right here.
When may.
So, Vincent, a lot of the Internet of Things are also connected with the local area network, with the Wi-Fi, LoRa. So, how much of this also apply to the local area network?
Yeah, so the question was how much of this also applies to local area network, since a lot of Internet of Things, like my doorbell, for example, at home, is connected to a Wi-Fi network. Well, I mean, the basic principles are the same, okay? Except that there, with a Wi-Fi network, you have infrastructure. So some of the issues are not there. And some of a lot of the latency, for example, is going to be in the network rather than in the point-to-point. On the other hand, if you can still have peer-to-peer Wi-Fi, and you have some of the same issues. So I think it's, in principle, it applies everywhere, but in practice, for those kind of things that are communicating up through an access point, you may not be as worried about some of these things. So.
Okay. Yes, another question.
Fascinating talk. So you mentioned latency and other layers of the network. Do you think that block lengths encoding are a bottleneck in latency in some applications, or are other layers more important?
Well, I sort of glossed over it at the end, but it just depends on how much infrastructure you have, right? In peer-to-peer communications, it's all about two things. One is the block length, right? And the other is things like synchronization and so forth. So which of those is the bottleneck depends a little bit on the application. In infrastructure networks, where you're going up to an access point through the network and back down, then it's not clear what's the bottleneck, right? This is really only addressing the physical layer, and then that's what when I mentioned that we need to think about interactions with other layers before we look at the overall latency. Yeah.
Okay, so before closing, I want to present something to our speaker as
it's an orange
appreciation,
box.
an orange box, and
Yeah.
thank you very much.
Thank you very much. Thank you for coming.